what did we learn from all of this? Even though we had great results, we actually risked cutting off the horror factoring entirely because a decision on what to do was taken before having the data to confirm that there was a problem on the implementation and what it was exactly. So without data, we couldn't find an issue just by looking at layers and layers of obscure code. So we were basically blind. Another thing that we learned is that it's always a good thing to also have internal people dedicated on such delicate and important part of the business, because changing hands in those parts of the code base can result in loss of consistency and robustness very quickly over time, which in turn results in losing revenues.
Okay, so hello everyone, and thanks for being here. Today, me and Davide are going to talk about our advertisement stack evolution and what positive impacts these changes brought, both for performance and most importantly, for revenues. But first, we need to introduce ourselves. I'm Fausto, Android engineer, working in Subito, currently in the ADV team.
And I'm Davide, and also an Android engineer in Subito. I've been here for around a year and a half, and I'm taking care of the search and transaction side of things.
Before diving into the talk, we would like to introduce our company, Subito, which is part of Adevinta, a global online classified specialist operating digital marketplaces in multiple countries. We provide technology-based services that connect buyers with sellers and facilitate transactions from job offers to real estate, cars, consumer goods, and more. Subito has been established in Milan in 2007, and we are currently strong positioning among the top 10 most visited online brands in Italy with 13 million users every month. Throughout this speech, we are going to use certain terms that we are going to explain shortly. The first of this is ADV. ADV stands for advertisement and is, for example, a banner that can be shown to the user in an app. They are usually rendered by ADV libraries using a web view. Then we have an AD server, but simply for a case, an AD server is a technology that allows advertisers to handle an inventory of ADVs that can be provided across clients that request them. Then we have the AD unit. Basically, the AD unit is the space in an app which you can use to load an ADV from the AD server. Then we have the fill rate. Well, technically, the fill rate refers to the capability of an AD server to provide an ADV for that ID unit. Given that a publisher, of course, decided to buy that space. Basically, when an ADV cannot be provided, the fill rate goes down. And then we have RPM, which is page revenue per 1,000 impressions. Okay, in this talk, we're going to focus on two specific parts of the Subito app. That are the main sections in which the ADVs are shown to the user. That is the search results page, which we'll refer to as listing, and then the results detail page, referred just as detail. So what is this about? Like many others at Subito, we are also using ADVs to sustain our business. One day, we were looking at the performance and business metrics of the web ADV stack implementation, and we noticed that they were underperforming. They were loading slower than we expected, but also they had a low fill rate, which means that for some reason, publishers didn't buy ADV spaces as much as we expected. That is, we had empty ADV spaces. So we took a look at the web ADV stack implementation and decided that we needed to refactor, which in the end had a positive impact on the aforementioned issues, and we were happy for a while. Well, not so happy, but anyway, until we weren't. We started collecting some data on the Android and the iOS ADV stacks, and noticed that they were also underperforming. Since data on the app didn't look as bright as the new web implementation, our business people saw that on the Android side, we were performing less than the new web implementation, which was odd given that usually our apps are performing higher than the web client under many aspects. So the Android ADV implementation needed some love, basically. And we decided that, why not, we needed to refactor on Android too. Well, we also decided that we needed to refactor on iOS, but we don't do that here. Now, I want to introduce you to how our stack for loading ADVs should work. The actions that we need to take in order to retrieve and show ADVs start with the client getting the bids from various bidding partners for a particular AD unit, which return their available bids to the client. Then the client requests an ADV from the ADV server, which in our case is Google Ad Manager, with the targeting attributes coming from the bids, so that we can get the available ADVs that can be used to make the auction locally and return the winning bid. Finally, the winning bid gets shown to the user as an ADV. Oops. That's you.
Yeah, thanks. Okay, so before analyzing what our issues were, we knew that we had some missing analytics, and unlike with the web client, we had no technical debug or performance events. We had a really low fill rate, as Fausto said. ADV spaces weren't being filled with ADVs, but without data, we didn't have an hint of where the problem was. And last but not least, there was a lot of old code. The old implementations was written by many hands, and most of them weren't part of our company anymore, or were external people that also weren't part of our company anymore. So it wasn't maintainable and lacked coherence between different parts of implemented layers, making it really hard to pinpoint a supposed issue. So we decided to collect the missing data on the simpler case, which for us was the detail screen. The data that we collected are the time between the page landing and the ADV being shown, the time between the ADV creation and the ADV being shown, the time to request and load an ADV, the event of success and failure with the detailed reason of failure, and last, the event of the ADV being viewed. Going straight to the data that we collected on Firebase, as we previously said, we noticed that we had some slow loading times. For example, we can see that the average on the 90th percentile was around 7.5 seconds with a 3 seconds median. Also, by collecting the total time it takes for an ADV to be shown, meaning from when the user lands on the screen to when the user actually sees the ADV, told us that too many users were not seeing our ADVs at all. And it took an average of almost 11 seconds for an ADV to get shown to the user with a little bit more than a 3 seconds median. By putting all of this data together, we noticed that, again, the landing to shown time of our details top banner took a huge amount of time, sometimes even bigger than the loading time itself. This told us that something wrong was going on with the visibility of the loaded ADV, because we expected that after loading the ADV, we should be able to see it right away. On top of that, the detailed top ADVs banner had less views than loading success events, which, as we saw earlier, confirmed that the ADV wasn't being shown correctly after being loaded. In addition, by looking at the analytics events, we saw that the vast majority of the errors were in fact unable to fill errors, which just confirmed what we already knew, that we had a really low fill rate.
So after watching the data, we could start to investigate and pinpoint the actual issues in the ADV stack code. Earlier, we suspected that there was something sketchy going on with the visibility of the ADVs in the detail screen. By looking at the code, we could see that there was a bug in how we decided to show the ADVs. In fact, the top ADV, as you can see in the detail screen, was being shown until a scroll gesture happened. But this wasn't so obvious, because we already had issues with the low fill rate, so sometimes ADVs just didn't show at all, so it was a bug hidden by other issues. Another problem that we found in the code was that the ADVs weren't added to the view hierarchy as soon as possible. So instead of the ADV being shown exactly when it was ready, we were losing more time to, after loading, to actually show it. Also, ADVs didn't start to load as soon as possible, but instead we waited to create all the view blocks. You see, since the UI is built from an array of UI blocks that are sorted by how they should appear, the ADV UI blocks had to wait the previous UI blocks to be created before starting to load. Unfortunately, for that reason, the detail screen layout is based on a scroll view, instead of a more optimized layout like a recycler view or a lazy list. So every single view is rendered instantly and not lazily. The way it works is that depending on the ad that we need to show, we map different types of blocks and render them. So converting all those blocks to modern standards would have taken too much time because we currently have like more than 40 different blocks, and it will require a full refactor of the entire detail UI. Also, to add more to that, our ADV views were wrapped inside more container views that were taking unnecessary time in the creation process. Lastly, ADVs started to load all at once, which intuitively will make you think that that is a good thing. But in our case, actually made loading slower. And we are going to explain why. The issue is that when trying to load more than one ADV concurrently, internally, every single ADV has to go through some kind of AV initialization. But since we didn't have access to the inner workings of our ADV library, we couldn't really know what was happening. Here you can see, for example, let's say that one single ADV takes 2 seconds to load. That also includes, say, time for the initialization. We saw that loading more than one ADV at once took about the same time for each of them, but in reality, it took more than the time for just one ADV. So we experimented by trying to load each of them one after the other, sequentially, basically. What we found was that by loading the ADVs sequentially, the first was still doing the initialization step, but every next load was faster and faster. This means that we could load the first ADV as soon as possible, and this was important because that is what the user sees after landing on the screen, but also it made the other ADVs load much faster, so that by the time the user scroll down, they will find the other ADVs already shown and ready.
So based on all these points, we were able to test how much some of these things impact our loading times. So we decided to create a proof of concept, a newly implemented ADV that was meant to fix part of the issues that we saw. In particular, with the new implementation, the banner was added immediately to the view hierarchy. So as soon as it loaded, it was being shown. And this fixed the scrolling issue that we saw earlier. And also, since ADV SDKs already provide an ADV view that is ready to be used as is, we didn't wrap the ADV inside other unnecessary views. What we couldn't fix at first was fixing the fact that they were loading all at once, or that they didn't start loading as soon as possible. With that in mind, we managed to come up with a plan to let another structure handle the loading and the providing of banners for us, as opposed to managing the banners singularly at the business logic level of each screen that had banners. We introduced a system that will exactly do that, which we named ADV Banner Pool. Since long-term pre-caching of ADVs is a best practice, the pool was going to get instantiated for each screen that didn't banners, so that we could cache ADV short-term for that specific screen, and use them immediately or within a short time inside the screen where we needed them. The first thing that we're going to talk about is like the setup method. We decided that the pool was going to have a limit of ADVs that could be cached in memory. So we made this method. This is because we wanted to allow a refresh of ADVs in case the user will scroll far down and then scroll back up, but also because we didn't want to clog the RAM with unnecessary ADVs. Then, since we always know where each ADV is meant to be mapped ahead of time, we added a method to input such placement mapping so that they can start to load to hopefully be ready as soon as possible for the user to see. Basically, we tell the pool that, for example, at key 0 or whatever, there should be a particular ADV unit that should be loaded if needed. We have the placements. Now we need to get the actual banner. So this is the method that retrieves the banner given the key. A key can be anything that you decide. It could be an integer or a string, for example. It doesn't really make that much of a difference in terms of functionality. It's just used as an ID. In our case, we had integer keys, and each key is the position of where we know the ADV is going to be mapped to. Given a key, if a placement has been mapped for that key, an ADV is returned. That ADV is ready to be immediately added to any hierarchy of views. Within the set memory limits, an ADV will always be ready, already loaded when returned. Otherwise, a loading and caching mechanism will occur, and the ADV then will be shown as soon as possible. Set limits are always enforced with a mechanism to dispose of the oldest ADV memory, which typically is already far off screen. And finally, last but not least, since the pool should be used as one instance per screen, we added also a cleanup method that takes care of freeing all the banners in memory. With this implemented ADV banner pool, we could now handle the load of requested banners ADV as a queue. The user of the pool should just have to worry about retrieving an ADV and adding it to the view hierarchy, as the loading is handled internally and consistently for all of our use cases. This way, we could finally fix the last 2 points that we couldn't fix at first. We could load them as soon as we wanted, independently from the life cycle of the screen, and also we could take advantage of the fastest loading mechanism for the multiple ADVs. All of this loading strategy became most useful in the listing section of our app, where on initialization of the ADV banner pool, we assign a max number of banners in memory, enough to be safe to have the right amount of preloaded ADVs, and let the user scroll without having to continuously load more ADVs. What you're going to see here is the simple schema of the mechanism that takes place when a list of search results is returned from our endpoint. First, the user, let's say, perform a search with a query, and this query is sent to our server, which returns the search results to the client. Then the client computes where the ADVs should be placed and uses those positions to merge the ADV items in the results list. And finally, the search results with the ADV items can be rendered by the list adapter.
After all this technical stuff, we are now going to talk about the results, both in terms of performance and in terms of revenues, as we said at the beginning of this speech. First, we will talk about the tech performance metrics, starting from the detail screen. Again, note that the top ADV is the one which the user always sees when landing on the screen. As you can see from these numbers, we made sure that the user saw the first ADV much faster, with an average loading time reduced by 45%. But also, the average loading time of the middle ADV improved by more than 68%, just because now we are loading it after the first. Furthermore, by looking at the top ADV average loading times on the old versus new implementation, we can see that they improved by a lot. They are much more consistent, but also lower. Just to give you some numbers, on the old implementation, the average was 8.4 seconds, while on the new implementation, the average is now 6.4 seconds. Of course, we had interesting results in the listing page too. Also, in this case, we're looking at the data about the top banner, which is the first one that the user sees. Even though we had similar results on the other placements too, of course. Although the improvement is a lower 29%, this is just because the listing screen didn't suffer from some of the issues that the detail screen suffered. So the performance of the banners was already better, but we managed to still improve it to the maximum we could potentially do. Moving forward, we're going to take a look at some of the results regarding the revenues. We got the first results after fully going to production with the new stack in March 2023. Compared to last year, we got a 17.5% increase in revenues from ADVs. Comparing Q1 year over year, we got a 19.4% increase in revenues. Furthermore, in February 2023, before the new stack was released in production, Android made 12% of the total revenues, while iOS made 9% and web made 79%. We also collected fill rate data, and as you can see on the right, this was our baseline for comparison, so that we will see how it improved alongside the share of revenues. In March 2023, after we released the new stack, Android made 22% of the total revenues, while iOS made 12% and web made 66%. Again, on the right, you can see that on March, the fill rate improved by 267%. This huge increase is just due to the fact that it was really low in February. So what we're really seeing here is that we brought it back to acceptable levels, normal levels. Finally, in September 2023, Android IDVs made 29% of the total revenues, while the fill rate also improved by 32% relative to March.
So, what did we learn from all of this? Even though we had great results, we actually risked cutting off the refactoring entirely because a decision on what to do was taken before having the data to confirm that there was a problem on the implementation and what it was exactly. So that was the first lesson that we learned right away. Always add the data that supports an important decision, such as refactoring large part of the code base. Because the code base of the ADV stack was very old and with a lot of layers accumulated from year to year by different hands. So without data, we couldn't find an issue just by looking at layers and layers of obscure code. So we were basically blind. Another thing that we learned is that it's always a good thing to also have internal people dedicated on such delicate and important part of the business, because changing hands in those parts of the code base can result in loss of consistency and robustness very quickly over time, which in turn results in losing revenues, of course. And that's it for today's speech. And thanks everyone for listening to us.
Thanks.
And thank you. If you have any questions, now is the right time to ask them.
Thank you guys for your talk.